A 2.9 millihenry toroidal solenoid has an average radius of 5.4 centimeters and a cross-sectional area of 2.2 square centimeters. Blah blah blah. How many coils does it have? In calculating the flux, that B in a uniform cross section, neglect the variation of B with distance with toroidal axis. Express your answers in numbers of turns. What rate doesn't change given this of current with respect to time given 2. Okay. There's a lot going on in this question. We're going to start by drawing a picture and we're not going to really solve it directly. We're just going to solve everything and basically just give them the answers they want. So long story short, what's going on here is we have a toroid, a donut. This donut has coils wrapped around it. And when it says, assume that B is uniform across the cross-sectional area, basically, this is like a solenoid that's kind of wrapped around on itself. But the magnetic field on the inside is going to be stronger than the magnetic field on the outside. It said just consider everything to be the same, which makes our life reasonable and much more possible. They also talk about millihenries. So I'm going to say L is 2.9 times 10 to the negative third henries. So that's inductance. Then yep. And the rest they want us to find. So there's a lot going on here. So to start with, I'm going to say that EMF, induced EMF, is negative d flux dt, the derivative of flux with respect to time. And flux is the area, the magnetic field dot the area vector. In this case, since the magnetic field is going this way, the area vector, the area is just going to be these cross-sectional areas here, and so the area vector is going to be here. We're going to say that the area vector, which is kind of like that, it's I'm going to say perpendicular to the cross-sectional area of our donut, toroid. And the magnetic field basically goes along with it. Long story short, the parallel dot products are a measure of how parallel two vectors are. They are parallel. So I am going to simplify this to derivative with respect to time of magnetic field times area. Almost always happens that way. Sometimes it doesn't, usually does. So then we have the derivative of two variables here, magnetic field and area. So we do the product rule, dv dt times area plus magnetic field times change in area with respect to time. This toroid isn't getting bigger or smaller with respect to time, not, fluctuating up and down. Therefore, the change in area with respect to time is 0. That portion right there, 0. And so we're left with change in magnetic field with respect to time times area. And that's going to be the induced EMF, which is volts, measured in voltage. So sometimes people will just write V for voltage for that. Okay, so now we got to this point. What we want to know is what's the magnetic field with respect to time? That comes from a different law. So this is, I think, Faraday's, maybe Lenz's. They're both related. One tells you direction. I think Lenz tells you direction. Faraday's law tells you magnitude. Doesn't matter. This negative symbol, which I dropped tragically, it doesn't matter because we care about magnitude, is Lenz's law. All right, game face, focus. Amperes law. So B dot dl equals mu naught, which is just 4 pi times 10 to the -7th constant, times I enclosed. And so what we do for this is we have this coil that's wrapped like a donut. That's, yes. And what we do is we do a enclosed shape, that's a circle, enclosed loop, that's a circle, and that is going to be our integral.dl. That's the path, the integral that we're integrating along. It's a closed path, and the I enclosed is going to be the current from each of these wires. So the number of wires is n, because we're just going to say n number of loops, n right up there. So n times current is how much enclosed current we're going to have basically going through this loop here. So long story short, magnetic field we assume is constant, so we can pull that outside of our integral. So we have B integral dl equals mu naught I enclosed, which I'm going to rewrite as n. That's supposed to be an n times current. So the idea here is the total enclosed current is going to be each of the individual wires times the number of loops. This length here, the length of our path here, since we're just going around our donut, is just going to be 2 pi r. Long story short, magnetic field inside, I'm going to do TOR for toroid, is going to be mu naught n times I over 2 pi r. Now, this is very similar to the magnetic field due to a solenoid. This is just going to be like a sidebar for understanding. Magnetic field solenoid is mu naught n I over L, where L is the length of your solenoid. Well, if you think of the toroid is basically a solenoid folded in the shape of a donut. So if you think of the length, it's going to be the perimeter of a circle, which is 2 pi r. Seems reasonable. So long story short in life, if you have to memorize something, memorize the magnetic field for a solenoid. That way you can be like, oh, for a toroid, I just use the perimeter for the length. And it's good to know that Ampere's law exists and that it can be done, but you probably won't need it. All right, so we have magnetic field due to a toroid. So now what we need to do is we need to take the derivative of that with respect to time, because this equation right up here is what we're going to work with. So let's see here. Let's try. Actually, I'm going to find dB. I'll do a little TOR here just so we know it's toroid. dt. Now, when we look at this, I can't remember what that constant's name is. That constant, it's constant. N, number of loops, constant, 2 pi r, constant because it's not, the toroid's not shrinking or looping. So this is just going to be mu naught n over 2 pi r times di dt, where di dt is going to be the change in current with respect to time. Yep, I'm good with that. And so now we're going to apply this to this equation we have up here. And so we're going to have the EMF, which is the same as voltage, equals dB dt, which is mu naught n over 2 pi r di dt times area. Now, one thing that I forgot to mention here, neglected, failed, was this is area total, which I should have written up there. Area total, that's the total area of every one of these loops. So these have a whole bunch of loops, bunch of coils, and we want to view them each as an individual. So long story short, I'm going to say that this area total is actually equal to A times N, because we had to look at the cross-sectional area of each individual loop and multiply by that by the number of loops that we have. So that was a oversight, human performance trap that I set you up for. My apologies. All right, so now this becomes, instead of A, we're going to look at that as A total, which will be the same as individual cross-sectional area times N. Okay, so now we got that. Rearrange this, make it a little bit prettier. Let's say mu naught n, 2 pi r. We've got 2n, so we'll call that squared. Multiply this by A, and then we'll put di dt over here. The reason I wrote it this way is this gives us to the definition of inductance. So they give us an inductance, Henry's. That's what Henry's measures. It's a measure of inductance. They even say here self-inductance. The definition of inductance is E equals L di dt. And so if we look at it this form, there's the E, epsilon, the EMF, voltage. Here's the current. And then right here, that's going to be the self-inductance of a toroid. So that's where we got our definition. All right. Now we have everything we need. Do they give us a change in current with respect to? No, they don't. But they do give us a inductance. All right. So we're going to take this sidebar. Time to answer question 1. The self-inductance for a toroid, so the little tor right there, so we know, is going to be mu naught n squared a over 2 pi r. We want to know n, so we're going to rearrange this. We're going to say that n squared is L. I'm just going to drop the tor. No, I'll write it in. You're right, I should. 2 pi r. And I should keep the r's consistent. I did not. Mu naught times area. So I'm going to copy and paste this up near the problem statement. That way I have all my numbers available. So this becomes 2.9 times 10 to the negative third times 2 times pi times r, which is 5.4 times 10 to the negative second. I know my handwriting is terrible. I am sorry. 4 pi times 10 to the negative 7th, because that's just what mu naught is. And then the area is 2.2 centimeters squared. So I'm going to write that as 2.2 centimeters squared. And then for centimeters squared, I'm going to do 10 to the negative second times 10 to the negative second, because I converted both centimeters squared to meters. Yes. And the idea there is because we have to do it for each of them. All right. So now I'm just going to rearrange this. We'll do 2.9 times 2 times 5.4 times pi times, and this is going to be 10 to the negative fifth, because we have negative 3 and negative 2, divided by 4 pi times 10 to the negative 7th times 2.2 times 10 to the negative, I'm going to cross out the negative 7. Negative 7 and 4 is negative 11. This becomes 10 to the negative 6, which is 10 to the 6 up top. I know, lots of math might not be worth it. We'll see. So now I'm going to rewrite this one more time. So we have 2.9 times 5.4 divided by 2 times 2.2, which is 4.4, times 10 to the 6th. That feels kind of high. Maybe. Oh. Nope, I think I'm good. Negative 3, 10 to the negative 7th, area. Yeah, let's go with that. Let's see what happens. So then, calculator. Move it over here. On 2.9 times 5.4 divided by 4.4 gives us about 3 times 10 to the 6, which is many, which might be true. So this is, and this is not n, this is n squared, which is the key idea here. And so when we go back to our second square root, second answer, that gives us 1887. N equals 1887 turns. So, I'm gonna bring this down here. Paste right there. So all the messy work we did with actual numbers up there, 1887. Okay, so I'm gonna write that in real quick, just so I have it available. 1887, plausible. Then ask, at what rate must the current change? Current through it change through potential of this to develop that across its ends. Okay, so for this problem, we are just going to go straight to this equation right here. So this is the definition of inductance, and we want to know di dt. So di dt is going to be the EMF divided by the inductance, and so this is going to be 2.6 divided by, I see it's just volts, yep, divided by 2.9 times 10 to the negative third, divided by 2.9 times 10 to the negative third. I can take that 10 to the negative third, make it 10 to the third up top. So this is going to be 2.6 divided by 2.9 times 1,000. And that's going to be about, I don't know, 850 maybe. 2.6 divided by 2.9 times 1,000. Yeah, closer to 900. So 897. 897, and that's going to be amps per second. 897 amps per second. Write that up. Whoop. 897 amps per second. Okay. So, recap what we did here. I'm going to move all this mess to the side because we don't want that to distract us from the bigger picture. Whoop. So, we were asked a whole bunch of things, and I basically ignored much of the problem statement and just was like, all right, solve for everything. So they gave us the inductance of this toroid, this shape. And the inductance is going to be due to basically the geometry of the shape. The inductance, we kind of derived, we did derive it using Faraday's law, Lenz's law, Ampere's law, everything we know. Each step isn't big, but when you put them together, it's kind of difficult. Most people will probably jump straight to this step. You're probably going to be given the inductance of your shape, like the equation for the inductance. And so for a toroid, this is going to be your inductance, and you'll probably be given this. If not, don't panic. You can find it. Probably won't have to. So you're given this. You solve it for n squared, you put in your values, you square root your n squared to give yourself n, and bam, that's your first answer. After that, they ask you, all right, what is the changing current with respect to time? And you're like, okay, the definition of inductance is EMF, which is equal to L di dt, change in current with respect to time. We want to find di dt, so you just rearrange it. You're given everything else, you plug in the numbers, get the answer, and you move on. So this is one of those questions which is reasonably difficult, though doable, and it's worth understanding, but with a test scenario, it'll probably be easy. It'll be like, here's the formula, apply formula, here's the formula, again, apply formula. So, can be high stress, doesn't need to be high stress. Do what is appropriate for, if you're timed evolution or doing homework. All right, hope that helped. See you next time.